On October 9th, 2022, a burst of light hit Earth. Not just any light, gamma rays, the most energetic form of radiation in the known universe. And they were arriving faster than any detector could properly respond to. Satellites slammed into saturation. Instruments that had spent decades cataloging the sky were momentarily blinded. The signal was so extreme that it was later detected retroactively even by Voyager 1, a spacecraft more than 14 billion miles away at the very edge of the solar system. Astronomers gave it a name, the B.O.A.T, the brightest of all time. And it came from the birth of a black hole. Before we get to what that burst actually was, let's talk about something that sounds impossible. In the 1970s, astronomers using a technique called very long baseline interferometry, essentially connecting radio telescopes across continents to act as a single enormous dish, started looking at the jets coming from distant galaxies. These jets are narrow, focused streams of plasma fired from the vicinity of supermassive black holes. And when they measured the apparent motion of material inside those jets, something came back wrong. The numbers said the jets were moving faster than light. Not slightly faster. Some of them appeared to be moving at 6, 10, even 25 times the speed of light. Now, if you know anything about Einstein's special relativity, you know that's supposed to be impossible. Nothing with mass can reach the speed of light, let alone exceed it. So either Einstein was wrong, or something else was going on. Einstein was not wrong. What the astronomers had stumbled into is called superluminal motion. And the strange thing is, it had been predicted. In 1966, the British astrophysicist Martin Rees worked out the geometry and published a paper saying, essentially, if something moves fast enough and points close enough to directly at you, it will appear to exceed the speed of light. 5 years later, VLBI confirmed it. Here is what's actually happening. Imagine a jet of plasma pointed almost directly at you, not firing sideways across your field of view, coming toward you at a very slight angle, moving at 99% the speed of light. As the jet moves toward you, the light it emits has less and less distance to travel to reach your eyes. Each successive flash arrives a little sooner than the one before. The jet is chasing its own light. And when you reconstruct the apparent motion from all those arriving signals, the object looks like it covered an enormous distance in almost no time, faster than light. But it isn't. It moved at 99% of c, and the geometry did the rest. The galaxy M87, the same one whose black hole we photographed in 2019, has a jet with an apparent speed of about 6 times the speed of light. The actual speed? At least 99% of c. Real matter, moving as close to the cosmic speed limit as anything we had ever clocked. Until 2022. So how does a black hole fire a jet in the first place? Black holes don't let things out. That's the definition. So how is matter being launched away from one at nearly the speed of light? The answer isn't inside the black hole. It's just outside it. When gas and dust fall toward a black hole, they don't fall straight in. They form a disk, a swirling, superheated accretion disk rotating at relativistic speeds, heated to billions of degrees. Magnetic fields get threaded through that disk, compressed, twisted, wound tighter and tighter. They accumulate energy the way a spring does. Now add spin. A rotating black hole drags spacetime around with it. Physicists call it frame dragging. That rotation winds the magnetic field lines into a helical structure above and below the poles. And when enough energy has built up, those field lines launch plasma, electrons, positrons, ions, outward along the rotation axis at velocities approaching the speed of light. This is the Blandford-Znajek mechanism, first worked out in 1977. The spinning black hole acts as an electromagnetic generator, converting its own rotational energy directly into the kinetic energy of a jet. And the fastest jets appear to be locked to the spin axis of the black hole that launched them. A 2025 study in Nature Astronomy confirmed it. The most relativistic jets don't wobble, don't precess, don't drift. They are pinned to the rotation axis of the black hole. The jet is the black hole's spin, made visible. Back to October 9th, 2022. GRB 221009A was not a jet from a supermassive black hole in a distant galaxy. It was a star dying. Somewhere in a galaxy about 2 billion light-years away, a massive star, perhaps 40 or 50 times the mass of our Sun, ran out of fuel. Its core collapsed in a fraction of a second. The outer layers fell inward, then rebounded catastrophically outward. A black hole formed. And in that instant, the same mechanism that powers the jets of distant quasars switched on, but inside a stellar corpse barely the size of a city. The jet that emerged had an opening angle of barely 1.5 degrees, pointed almost directly at Earth. The Lorentz factor, the number physicists use to quantify proximity to the speed of light, may have reached the hundreds, with some estimates pushing close to 1,000. At the high end, a Lorentz factor of 1,000 would put the jet material at 99.99995% the speed of light. The kinetic energy released in those few minutes was comparable to what our Sun will radiate across its entire 10 billion year lifespan. Now here's where it gets measured. On a mountain in China's Sichuan province, at an altitude of nearly 14,500 feet, sits an observatory called Lhasa. It covers about 1 square kilometer of terrain and contains more than 5,000 detectors. It doesn't catch gamma rays directly. No detector on the ground can. What it catches is what happens when a gamma ray slams into Earth's atmosphere and triggers a cascade of secondary particles that rain down like a brief, invisible storm. The detectors read that storm and reconstruct what caused it. When GRB 221009A arrived, Lhasa recorded photons from it with energies exceeding 18 tera-electron volts. To put a number like that in context, the Large Hadron Collider, the most powerful particle accelerator ever built, pushes individual protons to 6.8 tera-electron volts. A single photon from a star that died 2 billion years ago arrived at Earth carrying more than twice that energy. Not a beam of particles, not a controlled collision, one photon. Statistically, events like this happen once every 10,000 years. We happen to be looking. And Voyager 1, 45 years into its journey, now deep in interstellar space, picked up the signal too. Black holes are described as the ultimate endpoints. Things fall in, nothing comes back. And that's true for anything that crosses the event horizon. But the black hole's influence, its spin, its gravity, its capacity to warp space-time and wind magnetic fields to breaking point, extends well beyond that boundary. And what it does in that region just outside the point of no return is hurl something back at the universe harder than anything else in nature has managed. One of the most extreme natural outflows ever measured did not come from a laboratory machine. It came from a dying star. From a black hole doing what black holes, when the conditions are right, actually do. Not just swallow. Sometimes they throw back. If this kind of physics has you wanting to go deeper, we've linked some books in the description. See you in the next one. Thanks for watching.